All right, so in these video notes, we're going to talk a little bit about chemical bonding. So we're going to see how we actually bond elements together and write the chemical formula and deal with some of the naming stuff a little bit later on. Okay, so you will need your periodic table for this. We're going to basically be using your periodic table for this entire unit. So we're going to go over a couple of things real quick just before we get started. So chemical bonding, so we're going to go back up here to our periodic table. So one thing you have to know is your valence electrons. Okay, so right here we have 8 valence electrons in our noble gases. Then your halogens had your 7, and then we have 6, 5, 4, 3. We're going to jump all the way across here to 2, and then 1. Okay, so that's going to help us determine our charge, which is how we basically bond with another element. Okay, so again, that is a very key aspect to what this whole unit is about. And so again, with these notes, video notes, feel free to jump around these all you want. If there's something I'm talking about that you feel are comfortable knowing, you already know, then feel free to fast forward to examples if you need anything like that. So don't feel like you need to watch the entire notes. It's kind of up to you and here to help you. Okay, and just again, refresher from the last video, remember we have our metals that are going to be on the left side of this staircase. So basically anything going to the left of the staircase is going to be considered a metal. And then some of the elements that are on the staircase, like boron, silicon, germanium, arsenic, antimony, tellurium, and polonium, those are going to be your metalloids. And then basically everything else to the right of the staircase is going to, all the way over here, is going to be considered a non-metal. Okay, and so we'll kind of talk about that here in a second. So I just wanted to do a little recap. And so let me clean this up. And then we'll get started. Okay, so chemical bonding. So we've got, what is chemical bonding? So this is basically when electrons are shared or transferred between two or more atoms. Okay, so again, remember electrons involved are only the valence electrons. So you have an atom that looks like this, okay, and you've got these energy levels that are around this atom. Okay, your outermost level, that's where these valence electrons are going to be, and those are the ones that are going to be involved in bonding. Everything on the inside, so like these core levels, has nothing to do with the bonding at all. Okay, because they're closer to the nucleus and they're shielded from these outer electrons. So they basically have nothing to do with chemical bonding. Now, why do atoms bond? Is atoms typically bond to form an octet in their valence level. So remember that octet rule is they want to have 8 valence electrons. That's the perfect number. Okay, so think of that as something that you need to have. So they're going to bond with somebody to make that happen. Okay, and why that happens is it makes them stable. So basically it's something that they're missing and they want to become stable. Okay, then you have a term called intramolecular forces. These are the attractions within a molecular compound. Okay, so if you have something like H2O, okay, there are intramolecular forces that are holding that H2O together. Okay, same thing with something like CO2. Okay, there are intramolecular forces that are holding that compound together. Okay, so intra means within. Okay, so within that one compound, okay, that's what's holding it together. Okay, so ionic bonds is the first bond we're going to talk about. That is between your metals and nonmetals. So remember, we just recapped what that meant is metals are going to be on the left side of the staircase and your nonmetals are going to be on the right side of the staircase. Okay, and these are going to be the strongest type of bond. Okay, because we're going to talk about it here in a second because your metals are going to have a positive charge and your nonmetals are going to be having a negative charge. Okay, and we know with things like magnets, opposites attract. So positive is going to be attracted to a negative. Now with ionic bonds, this is the transfer of electrons. Okay, so look at our example here. We have atom A and atom B. We have a metal and a nonmetal. So atom A only has 1 valence electron and atom B has 7 valence electrons. Okay, so atom B is 1 away from having that perfect octet. So what's going to happen is A is going to kind of get close to B, and B is actually going to take that electron from A and make that a perfect octet. Now, it's still considered A's electrons, so that's why it's still going to linger a little bit closer here, and that's what's going to create that bond between the two. Okay, so examples would be like lithium and chlorine. So lithium's on the far left side, chlorine's on the far right side, magnesium and oxygen, and then sodium and fluorine. So basically taking anything from the left side of the staircase and bonding it with the right side of the staircase. Okay, then we have covalent bonds. So covalent bonds, this is between a non-metal and a non-metal. The way I remember that is covalent means coexist. So they're both considered on the right side of the staircase. Okay, so the right side of the staircase, they still want to have an octet. But when you have a negative and a negative, okay, they typically don't really like each other because they're not going to really bond to each other. But what will happen is if they get close enough, the atoms will share the electrons. Okay, so they overlap their orbitals to share those electrons to make an octet. Okay, so again, your covalent bonds are going to be between a non-metal and a non-metal, and both of those are on the right side of the staircase. So ionic, back up here, was left side of the staircase and right side of the staircase, a metal and a non-metal, and covalent was both on the right side of the staircase, a non-metal and a non-metal. Okay, so examples would be like CO2, NO3, SO4, all on the right side. Okay, then we have our metallic bonds. So these are a little less common. We don't do a whole lot with metallic bonds. This is when there's a kind of a sharing of free-flowing electrons among a lattice of metals. This is what a lattice looks like. Okay, it's basically kind of like a grid that these metals are just going to kind of be around each other and just kind of share free-flowing electrons. So things are kind of just coming and going. Okay, so those would both be on the left side of the staircase, and that is not really what we're going to talk about a whole lot in this unit. It's mostly between ionic bonds and covalent bonds. Okay, so going back to the property of ionic bond, it is a metal and a non-metal. The whole goal is to get 8 electrons, and the non-metals are closer to achieving that goal. Okay, so remember, so your right side, they're a little bit closer to reaching that 8 electrons versus your far left side, like something like 1A and 2A, they have a long way to go to do that. So we're going to talk about why these bonds are made, okay, to basically help each other out. Okay, so metals are going to lose electrons and give them a positive charge. Okay, so say if I have something like hydrogen, okay, and it has a valence electron of 1A. Okay, so it means it has 1 electron. Now chlorine is going to have 7 valence electrons. Okay, so it's more likely that hydrogen is just going to give up that 1, then find 7, and chlorine is just more likely to find 1, then give up its 7. Okay, so if you're that close to 8, you're not going to give up those 7 electrons. So that is why your metals are going to be considered cations. Okay, because remember, if you lose an electron, so if this electron goes over here to chlorine, that means I lost something negative. If I lost something negative, that's going to give me a more positive charge. Okay, that's why it's called a cation. Remember, the way I remember cation is that there's a T in the middle. It looks like a positive sign to me. Then your nonmetals. So chlorine is going to take that electron from hydrogen to make an octet. Okay, so if I'm going to gain a negative charge, so if I'm going to gain something negative, that's going to make me more negative, which means your nonmetals are going to have a negative charge, and they're going to be called an anion. Okay, and the way I memorize that is if you've got 2 N's in anion, and so that means they're negative. Whichever way you need to memorize that, that's fine. Okay, so your metals are going to be cations because they lose electrons and they become positive, and your nonmetals are going to be considered anions because they gain electrons and become more negative. Okay, so properties of ionic compounds. So these are just properties of these bonds. They have high melting boiling points. All that means is since it's such a strong bond, it takes very high energy to break those bonds apart. Okay, they're hard and brittle as solids. Okay, so that means, they're hard, but they're also breakable, and they're non-conductors. That means basically you cannot really transfer electricity through them, okay, when they're considered a solid. Now, many are soluble in water, so it means once you put them in water, they'll dissolve, and when they dissolve, the free ions that float around these atoms, okay, those are conductors, okay? Those can conduct electricity. Those are known as your electrolytes. Okay, and then for lattice structures, okay, so again, lattice structures, these are basically these little kind of repeating patterns, and that's basically how these things can bond. So these properties, make sure you do know these properties because that's a question we can ask, is which of the following is not a property of ionic compounds? Okay, ions. So we just talked about that a little bit. This is simply when an atom gains or loses electrons. That means they're no longer neutral. Okay, so remember, a cation loses electrons. So we talked about that. The reason why it's positive is because it lost electrons, which made it more positive. So remember, if you lost electrons, which are negative, okay, that's going to make you more positive. And then anions are going to be considered negative because they gain electrons. So if you're drawing in something that's negative, that's going to make you more negative. Okay? Now your charges on your periodic table, this is probably the most important part when it comes to this whole unit is bonding. Okay, so we talked about valence electrons. Okay, so we talked about the perfect number is 8, and you can only have 1 through 8. Okay, so your group 1A has a charge of +1 charge, group 2A is a charge of +2 charge, and so forth. I'm going to explain these. Okay, the reason why group 1 has a +1 charge is because it's easier to give up that 1 electron than to find 7 or gain 7. Okay, so that basically, the way I remember it is like basically saying, hey, I have an extra electron, so here I have a +1. Who needs it? Okay, then group 2A is going to have a +2 charge. Again, it's easier to give up 2 than find 6. So it's basically saying, hey, I have an extra 2. Then you jump across here to that boron group, and it has 3. So again, it's easier to give up 3 than to find 5. Now group 4/4A can have a positive or a minus charge, -4 charge, because it can honestly go either way. Okay, you can gain 4 electrons, give 4 electrons. So that's why we're going to call it a positive or -4. Then group 5A, now you have more, now you're getting closer to those 8 electrons. So group 5A is basically missing 3. Okay, it only needs 3, so it's just going to find 3 versus giving up 5. Okay, so that's why I put it as -3, is basically it's, hey, I'm missing 3. Can I find 3? Group 6A has a -2 charge. So that's basically, hey, I'm missing 2. Group 7A has a -1 charge because it's only missing 1 because they have 7 valence electrons and only needs 1 more. Now group 8A is going to have a 0 charge because they have 8 valence electrons. They don't need anything, okay, so there is no charge. So real quick, we're going to go back up to my periodic table. So you need to have this down on your periodic table, and you need to know this. So remember, we give you a blank periodic table in the test. Okay, so you're not going to be given these charges. Okay, so I'll always start on the right side because I know my right side is going to be 0. Okay, because if you have 8 valence electrons, you don't need anything. If you have 7 valence electrons, you're missing 1, so -1. If you have 6, that means you're missing 2. If you have 5, it means you're missing 3. And carbon group can go either way because you're right in the middle, so it can be a plus or -4. Now we're getting further away from 8 electrons, so now the boron group is going to be a +3 because it's just going to give up those 3, then try to find 5. Now this whole center group, this transition metal group, we'll talk about here in a bit. Okay, those do not have a definite charge. We'll talk about those, how they can basically vary their charge based on who they're bonded with. So we're going to jump across all the way over here where we have 2A. So again, this is basically, hey, I have an extra 2. And then the last group is a +1 because they're just basically going to have 1 valence electron to give away. So again, you have to know these charges, and it will make your life so much easier if you can memorize this on top of the periodic table. So remember 0, -1, -2, -3, positive or -4, +3, +2, +1. Okay, so now let's go back down to where we were. Okay, so again, formulas are based on balancing these charges. The whole purpose of bonding is balancing those charges. Okay, so the positive charges must equal the negative charges, which is going to make a whole lot more sense here in just a second. So again, if you need to know where those charges are on your periodic table, you can rewind a little bit, or you can look at this chart right here to figure out what your charges are. Now, formulas. Okay, what I mean by formulas is something like this, like H2O. That's a chemical formula. Okay, CO2. That's a chemical formula. Okay, if we have something like magnesium chloride, that's a chemical formula. So we're going to figure out how we actually draw these out and make sure they're balanced. Okay, so we're going to start simple. Okay, so start by finding the charge of each element using a periodic table. So again, use that 0, -1, -2, -3, etc. Okay, because you will need to know those because that will determine how you balance out. So our example is sodium and chlorine. Now, if you write a +1 and a -1, that is totally fine. If you just write plus and a minus, that basically you're telling me that that imaginary number is a 1. Either way is fine. There's no wrong way there. Okay, so if you look on the periodic table, sodium is in group 1, so that means it has a +1 charge. Chlorine is in group 17/7A, so it has a -1 charge. Now, if the charges are already balanced, there is no need for additional atoms. So what I mean by that is if I already have a +1 and a -1, that's balanced, okay? You need to have the same positive as you do negative. So that means I don't need to add any more sodiums or any more chlorines to be balanced out. Now, when you do write your formulas, this is important. Your cations, which are your positive ones, are always first. Okay, they are always going to be first. So we are going to come down here. When you have a +1 and a -1, that means they're already balanced. So you just slap them together, and that makes it NaCl. So if you see right here, Na is your cation. That's your metal. Okay, your metals or your cations are always first. It will never be ClNa. Okay, that is completely wrong. Okay, so you always have to do your metals or your positive cations first. Now, once you do bond these together, you no longer need that +1 and -1. Okay, so you should not write it like this. So Na plus and Cl minus. Okay, because the whole purpose of bonding them together was to basically get rid of those charges. They want to bond so they can become neutral. Okay, so again, once those bond, the charges disappear. So it is simply NaCl. Okay, so here's some more examples. So when these are already balanced, so I have lithium with a +1, fluorine with a -1, so they're already bonded, so just put them together. So LiF. Now I have magnesium with a +2, sulfur with a -2, already balanced out, so just put them together, MgS. And the same thing with calcium and oxygen, they're both balanced, so you just put them together. So those are probably one of your easiest ones. So remember, as long as they have the same charge, like basically the same number, okay, you do not need to add any more of either one. Now, what happens when we don't have matching numbers? Okay, so one, we still need to find the charge of each atom before we can balance. So you're still going to use your periodic table to find the charge of each one. So if I gave you something like magnesium and chlorine, my very first step would be to look on that periodic table and see that magnesium has a +2 charge and chlorine has a charge of -1. Now, hopefully you can see that +2 and -1 are different. Okay, so that means they are not balanced. So our whole goal is to make them balanced while adding as little as possible. I don't want 17 magnesiums and 14 chlorines. Okay, I want to make this as easy as possible. Okay, and one of the ways you can do that is something called the crisscross method. Okay, sorry. When I put magnesium next to chlorine, I see that there's a +2 charge on magnesium and a -1 charge on chlorine. What you can do is you're going to take that 1 from the chlorine and bring it down to the magnesium, and you're going to take that 2 from the magnesium and bring it down to the chlorine. Okay, so that means I'm going to only need 1 magnesium, and I'm going to need 2 chlorines to be balanced out. Okay, so you always want to check yourself. So since magnesium has a charge of +2 and there's only 1 of them, my total positive charge would be +2. And chlorine has a charge of -1, and since there's 2 of them, I have a total charge of -2. So once these things equal, that means you're correct. That means it's done. So your correct answer would be MgCl2. So you are basically just balancing these out. Okay, so formulas for ionic compounds. So these are just more examples. So again, I have lithium with a +1 charge. So again, you can use plus or you can do +1. It's up to you. Okay, so I can see that there's a +1 charge and -2, so this is not balanced. So if you want to do the crisscross, you can take the 1 to the oxygen and the 2 to the lithium, and so that gives me Li2O. Okay, so always want to check, so make sure, so lithium has a +1 charge, and since I have 2 of them, that gives me a total charge of +2, and oxygen has a -2 charge, and I only have 1 of them, so that makes it a -2, so those match out. Now, if you get something like Mg +2 and N -3, you can still do the crisscross method, so just take the 3 to the magnesium and take the 2 to the nitrogen. So that's going to give me Mg3N2. Okay, so I want to make sure it's all balanced out. So since magnesium has a charge of +2 and I have 3 of them, so 3 times 2 gives me +6. And then nitrogen has a charge of -3 and I have 2 of them. And so -3 times 2 gives me -6. The numbers match out, and so that means this is balanced, a balanced formula. Now, crisscrossing, this is where you kind of got to be careful, is if you can reduce, you will reduce. So if I have something like Mg +2 and C -4, and you do the crisscross method, okay, so that means the 4 is going to go to the Mg, and C would go, and then the 2 would go to the C. Okay, it would give you something like this. Now we can see that they both share 2 as a common factor. So basically you're going to need to do is reduce that. So the correct answer would be Mg2C. So remember, the whole goal is to basically have as little of it as possible. Okay, so why would I have 4 magnesiums and 2 carbons when I can balance it out with 2 magnesiums and 1 carbon? Okay, so hopefully that kind of makes sense. Okay, now what happens when we mix a monatomic atom and a polyatomic atom? Okay, so remember the video I posted about memorizing polyatomics? This is where that kind of comes into play. So monatomic just means an element by itself. So like this calcium is considered monatomic. So mono means 1. Poly means many. Okay, so like NO3, hopefully you can see that there's more than 1 element there. That's what a polyatomic atom is. Okay, and so we can see that there is a +2 charge on the calcium and a -1 charge on the polyatomic, which is nitrate, and we can see that they're unbalanced. Now this is very important. You have to keep polyatomics packaged together with parentheses. So that means if I need more polyatomics, I will never alter this NO3. You leave that alone. Okay, don't touch it. That's the way it is. Okay, we have to keep it contained. Now we can still use the crisscross method. You can take the 2 to the nitrate, and you can take that 1 over here to the calcium. So basically that means I need 1 calcium, but I need 2 nitrates. So make sure this is what I mean by parentheses, because if you write NO3 and then you put a 2 next to it, okay, that makes it look like you're telling me that there's 1 nitrogen and 32 oxygens. Okay, that would be incorrect. Okay, so if I need 2 nitrates, I need you to put nitrate in parentheses so we don't touch that, and then you can put the 2 on the outside. So your correct answer would be right here. You have 1 calcium and 2 nitrates. So again, I cannot stress this enough, is you never touch anything on the polyatomic. Just leave it alone. Okay. Now, more examples. So if I have sodium with a +1 charge and then chlorate with a -1 charge, I can see that they're already balanced. So that means all you have to do is slap them together. There's no need for parentheses because I did not need any more polyatomics. Okay, what if I have hydrogen with a +1 charge and carbonate with a -2 charge? Okay, I can see that this is unbalanced, so I'm going to take that 2 from the carbonate over to the hydrogen, and then 1 over here to the carbonate. So that means I only need 1 carbonate. So I'm going to do H2CO3. So again, I did not need any more polyatomics, so I did not need parentheses. Now, if I have something like Mg +2 and PO4 with a -3, okay, so I'm going to write this one out right here. Mg +2, PO4 with a -3. I can see those are unbalanced. What I'm going to do is I'm going to do the crisscross. So I'm going to take the 2 to the phosphate, and I'm going to take the 3 to the magnesium. Okay, so that's going to give you 3 magnesiums, and I need 2 phosphates. So again, if you need more polyatomics, put it in parentheses first, and then you can have 2 of them. Okay, so that's very important, so make sure. Now, when it comes to crisscrossing, again, make sure if it can be reduced, it's going to be reduced. If I have Mg +2 and carbonate with a -2, if I take the 2 down to both sides, okay, I can see that both of them have 2. Okay, so they just reduce that back. So the correct answer would be MgCO3. So again, there's 2 ways you can look at that. Is I would see that they have a +2 and a -2 charge, so they're already balanced, so I just put them together. Now, if you do crisscross method, that's fine, but if it can be reduced, it needs to be reduced. Okay, now we're going backwards. So if I give you a compound, you have to tell me the charge of each ion in the compound. Okay, option 1 is find the elements on the periodic table. Okay, so if they're in group 1A through 8A, okay, they will always have that same charge. Okay, so group 1 will always have a +1 charge. Group 6A will always have a -2 charge. It never changes. Okay, so that's probably the easiest way is when you're dealing with groups like that I know they're going to be a constant, is just look at the periodic table. Okay, so NaCl is my first example, so I would find that sodium's in group 1A and then chlorine's in group 7A. So that means sodium has a charge of +1, so there's my first answer, and chlorine has a charge of -1. That is my next answer. Okay, then you have something like magnesium and oxygen. Okay, so I'd find that magnesium's in group 2A, which is a +2 charge, and then oxygen is in group 6A, which has a -2 charge. Okay, so that would be your answer is Mg plus 2 and oxygen with a minus 2. Now, you can do something like reverse crisscross. You can take the numbers from the bottom to the top. So my first example is if I have H2O. Okay, now if you do not see a number on oxygen, that's basically imaginary 1. Okay, so what I'm going to do is I would take that 2 up to the top of oxygen, and I would take that 1 up to the top of hydrogen. And you remember that your first element is always going to be your cation, which is a positive. So this is going to be H with a plus 1 charge, and oxygen is going to be a minus 2 charge. Okay, so that would be my answer there. Okay, now this method can be confusing when you're dealing with a reduced formula. So remember, we can have a reduced formula. So my example here would be something like MgO. Okay, so Mg, if I look, only have one of them, and I have one oxygen. So if you take the 1 to the oxygen, and you take the 1 to the magnesium, and you write Mg with a plus 1 and oxygen with a minus 1, that would be incorrect, because if you look on the periodic table, so again, always check your periodic table. If you look on the periodic table, magnesium is in group 2, which means it has a plus 2 charge. Oxygen has a charge of minus 2. Okay, so again, the reason why it's MgO is because it was already balanced, and all you had to do is put them together. So that's where a reverse crisscross can cause some problems, is if you don't check the periodic table to make sure that everything is correct. Okay, now how do we find the charges when dealing with a polyatomic compound? So my example is HClO3. Okay, so I have a lot of things going on here. Okay, so if you try the reverse crisscross method, you may get a little confused. Okay, so again, the 3 on this oxygen is a part of the polyatomic ion, meaning a ClO3 is 1 unit. Okay, so that means that 3 cannot be touched. So a lot of times what I'll see students do is when they do this, they'll do HClO3. They'll take the 1 from the hydrogen up to the chlorate, which that's fine. Okay, but then they try to take this 3 up to the hydrogen. And if you look at hydrogen, it's in group 1A, and it always has a plus 1 charge, so that means you are incorrect. Now, it's all about how you kind of look at this. That means if you have 1 hydrogen and 1 chlorate, so now if you put this chlorate in parentheses, that means there's only 1 of them. So that means I have 1 hydrogen and 1 chlorate. So the reverse crisscross method still works, but just make sure you do not touch that 3 on the chlorate. Okay, I only technically have 1 chlorate, so you can take that 1 up to the hydrogen and take the 1 from the hydrogen up to the chlorate, and that would be correct. So that means hydrogen has a charge of plus 1 and chlorate has a charge of minus 1. Okay, so and again, you can always refer to your polyatomic list if you want to make sure, because your polyatomics chlorate is always going to be ClO3 with a minus 1. So make sure to check your periodic table and your polyatomic ion list. Now something like MgSO4. So again, you cannot touch this 4. Okay, do not move it, do not do anything with it. You can't reduce it, you can't add more to it. It is always going to be just considered sulfate. Okay, so what I'm going to do is I'm going to draw a parentheses around this sulfate to basically contain it. That means 1 sulfate's there. Okay, so if I have a magnesium and a sulfate, first thing you can do is I can look on the periodic table and I can find magnesium is in group 2A, which means it's going to have a charge of plus 2. And sulfate is on my polyatomic list, and that's going to have a charge of minus 2. Okay, so again, this is where that reverse crisscross method can kind of come in to a little bit of confusion, is when you're dealing with a reduced formula. Okay, so that was the end of these notes. So the next video I'm going to do is I'm going to cover a little bit of the homework on how we actually combine these and come up with some of the names. And so hopefully this kind of helped a little bit.